All right, we're going to switch gears here, and now we're going to talk about these stressors. Stressors that you can apply to a chemical reaction that's equilibrium that's going to shift it in one direction or another. And what these look like are, this is called Le Chatelier's principle. And Le Chatelier's principle is just that if you have a system that's at equilibrium, you can disturb it. And there's things that you can do to disturb it that are going to shift that equilibrium. And it could shift it in the forward direction, or it could also shift it in the reverse direction. And some of the things that will disturb an equilibrium are obviously concentration change. So equilibrium is very sensitive to concentration. So if I have a system that's at equilibrium and then I just dump a bunch of one of the reactants in, that's going to shift that reaction. Since it's an equilibrium reaction, it's eventually going to come back to equilibrium, but it's going to get shifted in the inner. If I have a gas, gases are very sensitive to pressure, and so changing the volume, which would mean if I decrease the volume, that would increase the pressure. If I increase the volume, that would decrease the pressure. That's going to have an effect on the equilibrium. And if I heat something up, that is also going to shift the equilibrium, but that's going to be dependent upon whether I have an endothermic reaction or an exothermic reaction. So in order to know how temperature is going to affect equilibrium, I need to know something else about that chemical equation. Is it going to be an endothermic reaction or is it an exothermic reaction? So the easiest one to think about is concentration. What happens when you change concentration? And so if I take a really simple equation here, let's say I have N2O4, and that's in equilibrium with NO2. At equilibrium, my concentrations are constant because I'm at dynamic equilibrium. Now let's say I add in NO2 gas to the system. Now what I'm essentially doing is I'm increasing the concentration of this component here. What that does is that's going to reset my equilibrium, and it's going to shift the reaction in the reverse direction until it reaches that ratio between NO2 and N2O4 that's specific for this reaction. It's going to shift in reverse until it reestablishes that ratio. If I add in N2O4 gas to the system, now that's going to shift it forward until it reestablishes equilibrium. I can force a reaction to go forward if I add more reactant, or I can force a reaction to go in reverse if I add more product. I can also do this by taking things out. So if I remove NO2 gas from the system, now what's going to happen is if I remove this, now I'm going to shift my reaction forward because more of this is going to be produced until it reaches that ratio again. So this is going to shift it forward. This is going to shift it forward. This is going to shift it in reverse. And then also if I remove N2O4 gas from my system, this is going to shift it. If I remove this, it's going to shift it back here until it reestablishes equilibrium. So this is going to shift in reverse. This is not my initial concentration. This is not what's happening at the beginning. I have a system, I've let it come to equilibrium, and now I'm adding more of either a product or a reactant in, and that's going to shift that reaction temporarily until it reaches a new equilibrium, or I'm removing a product. And so a lot of times in industry, they'll do this when they have an equilibrium reaction and they want the product. Let's say you're producing ammonia and you want ammonia. So what they'll do is they'll set up the reaction, and then they'll have a way to remove ammonia from the mixture. And so you're continually forcing the reaction to go forward so that you produce more product by removing it from the system. So you're essentially stressing it so that it never is actually able to come to equilibrium. So that's kind of a trick that they do in industry to force more of a product to be formed. So that's concentration. So concentration you can affect in many different ways. You can either add more or you can take it away. If you have two reactants, you can add in concentration of what you can increase the concentration of one of the reactants, and that's going to still shift the reaction forward. Now the second one is volume, and volume has to deal with pressures of a gas. And so what you see is if I have a system and I've let it come to equilibrium, and then I suddenly compress that gas, now I'm increasing the pressure. If I increase the pressure by decreasing the volume, this is also going to shift the equilibrium, and it's going to shift it to the side of the reaction that has the least number of moles of gas. And so here in this example, you see I have N2 plus H2 to form ammonia. If I decrease the volume of that, this is going to preferentially shift the reaction forward until it reaches its new equilibrium, because there's less moles of gas that are going to be in there. So I have 4 moles of gas on this side, 1 mole of N2 for every 3 moles of H2. In that reaction, I'm going to form 2 moles of gas. So if I decrease the volume, I'm going to favor this. If I increase the volume, so I give it more space, it's going to favor the side that has the higher number of moles of gas. So in that way, for a reaction that has gases, I can shift that equilibrium just by changing the volume. Now, if there isn't a difference in the number of moles of gases, then it's not going to matter. Meaning that if I have a system where I have the same number of moles of gas as a reactant as the same number of moles of gas as a product, so let's say I have A plus B goes to 2C, now I have 2 moles of gas on this side, and I have 2 moles of gas on this side. So here, changing the volume will have no effect because neither one of these is smaller or larger. And so if I change the volume on this, neither side is going to be favored. Now, let's say I have a 2 here. So now I have 3 moles of gas on this side and 2 moles of gas on this side. Now my change in volume is going to have an effect. So if I decrease the volume, then I'm going to favor my product. If I increase the volume, I'm going to favor my reactant. I can look at the number of moles of gas that I have in my system, and that's going to tell me if a change in volume is going to shift this. So volume has only effect if you have a gas. If you don't have a gas, then volume is going to have no effect at all on your chemical reaction. Now the last thing, so this was concentration, this was volume. My last thing is temperature. And temperature is going to depend. It's going to depend on whether you have an endothermic reaction, meaning you have to absorb heat, or you have an exothermic reaction, which means you're releasing heat. You're releasing energy in the form of heat. So temperature, if I heat an endothermic reaction and I heat an exothermic reaction, it's going to shift them differently. So let's look back at ammonia. Now this is an exothermic reaction, meaning it's going to release heat. For these one, I'm trying to figure out how temperature is going to have an effect on the shifting of the reaction. If I see it's exothermic, that means I'm going to release heat. What I'm going to do is I am going to write heat in the reaction itself, just so I can keep track of where it's going. And then that helps me. If I heat this reaction, I'm going to treat heat kind of like concentration. If I take this mixture and I heat it up, since it produces heat, it's going to shift to the side where it's going to reduce the heat that it's producing. So if I add heat to a system and it's exothermic, so I'm increasing here, it's going to shift the reaction in reverse toward my reactants. If I cool it, so if I remove heat, I cool the system, now it's going to shift it toward my products and the formation of heat. So if it's exothermic and I add heat, it's always going to shift it away from where it's producing heat. If I remove heat, it's going to shift it forward to produce more heat. That's an exothermic reaction. Endothermic reactions are going to be exactly the opposite. So if we go back to, this is endothermic, meaning that it's going to need to absorb heat in order for it to happen. And so I'm going to add heat over here as a reactant because it has to absorb heat, and then there's enough energy for this to form NO2. So now when I add heat, it's going to have a different effect. If I add heat, it's going to shift it to the side that's going to be lower in temperature. So I'm going to shift it forward. I'm going to add heat, I'm going to shift forward. If I cool or remove heat, I'm going to shift it in reverse. So it has the opposite effect. So temperature is going to be dependent. If it's endothermic and I add heat, it's going to shift it forward. If it's exothermic and I add heat, it's going to shift it in reverse. So concentration is going to have the effect on everything irregardless. Volume is going to have an effect only on gases, and it's going to depend upon which side has the most number of gases. And then temperature, which is our third shifter or stressor, we call these stressors. Temperature is my third stressor. Temperature is going to depend on whether I have an endothermic reaction or an exothermic reaction. And what happens when you have an equilibrium and you stress it, whether it's concentration, volume, or temperature, you have a scenario where you have an initial stressor, then you have a time where this white area here, where you're reestablishing equilibrium, and then you come back to equilibrium, because these are equilibrium reactions. So these stressors are only temporary things that happen, and then the reaction will eventually come back to its equilibrium. And so you can see here, if I have this reaction here and I add NO2, so I'm going to add some of this product. I'm going to initially increase the concentration of NO2 because I'm adding it in, but then once I add that in, what I'm going to see is that NO2 is going to start to go down because I'm shifting the reaction back toward the reactants, and then I'm going to reestablish equilibrium, which means I'm going to see a little bit more of this go up as well. So I'm going to see this go up and I'm going to see this go down. So oftentimes these questions you're asked, what happens if I add NO2 to this system? If I add nitrogen dioxide to the system as a stressor, what is going to happen? What am I going to see? What I'm going to see is NO2 is going to go down. Even though I'm adding it, I'm looking at what happens after that initial stress. I add NO2, now what happens? I'm going to start to see NO2 go down and N2O4 go up because I'm shifting in reverse. If I did the opposite and I added N2O4, now what I'm going to see is N2O4 is going to go down and NO2 is going to go up because I'm shifting it in the forward direction. And so when you're looking at these problems and you're reading these problems, you're often asked at what happens right after you've done that stressor. Okay, so obviously if I'm heating a system and I'm asking you what's going to happen, if it's an endothermic reaction and I'm adding heat, I'm going to shift that toward the products. But if it's an exothermic reaction and I'm adding heat, I'm going to shift that back to my reactants. So I'm going to look at what's happening right after I add that stressor. So that is the end of this chapter. That concludes equilibrium. And like I said, this is really just kind of the basis for what we're going to do in the next two chapters. We're going to take this idea of equilibrium and we're going to apply it to various systems. We're going to apply it to acid-base chemistry in the next chapter. We're going to apply it to ionic solubility in the chapter thereafter. And so we're going to take this concept and these ways to calculate equilibrium, and we're going to be doing them over and over and over again. Okay, so this concludes this chapter, and I hope to see you guys in our Zoom meeting when we do our problems in class.